Thank you. Yes. Hello everybody. It's a pleasure to be here. I haven't been in Jerusalem in 30 years. It's changed quite a bit. Jerusalem and Israel have changed quite a bit in 30 years. It's quite amazing. And when I was here in Jerusalem the last time 30 years ago, I stayed in the Belgian house. I actually lived in the Belgian house. So it's delightful to be here again. We're having a meeting on complexity, and it's a very broad meeting on complexity. And broad enough that they've even asked me to come here and give a talk. So my subject is, most of you are concerned with physics, economics, biology, more practical kinds of complexity. I'd like to talk about conceptual complexity, complexity of ideas. And the main application of these concepts is actually in metamathematics. It's in talking about incompleteness and the limits or possibilities of pure thought, of pure reasoning. So that's a sort of an unusual area to find complexity, but it's there. So I think complexity is a very basic concept. Normally people think fundamental physics is either the very small, right, particle physics, high energy physics, or else the very large, cosmology. And in the middle we have complex systems like us that represent information and compute. And interestingly enough, also in pure mathematics, in the world of pure ideas, there is a lot of complexity. That's my subject. And also, besides that message, I have two take-home messages for you, two things to take home. One is that message, that pure mathematics contains irreducible, infinite complexity. And also that the complexity, of course, when it becomes a successful subject, you start looking back at precursors. And I would like to let you know that Leibniz, in my opinion, is an important name in complexity theory. This may come as a surprise. So I'd like to tell you some of that story today. And I have two other lectures later this week. So this is the prehistory of complexity. And the way I heard about this was reading Hermann Weyl, who was a mathematician, student of Hilbert, and a mathematical physicist. And Hermann Weyl has a number of books on mathematics, a number of books on physics, and two books on philosophy. And his smaller book on philosophy is called The Open World, and they were lectures he gave in 1932 at Yale University in New Haven. And there he talks about how important an idea of Leibniz about complexity is. He says it's really an essential concept, complexity, in the philosophy of science, in understanding what causality is, or what a law of nature is, or what a law of physics is. And the way that Hermann Weyl puts it is very dramatic. This idea of Leibniz, Hermann Weyl formulates it like this. He says, if you allow arbitrarily complicated laws, then the concept of law becomes vacuous because there's always a law. This is how Hermann Weyl puts it. You see? In other words, you're trying to distinguish between data that follow a law and data that is lawless. So you want to understand, what is this concept of a law? What does it mean to say, how can we distinguish a world which follows law from a world which doesn't follow law? So what is a law? What does it mean to say that something follows a law? And what Hermann Weyl says, if you allow arbitrary complicated laws, there's always a law. And then the notion of law becomes meaningless. So I think that's a good point. Now, how does Leibniz put it? Leibniz puts it a little differently. Leibniz discusses this in, Leibniz is a very interesting man, most of whose work was not published during his lifetime. It was found long after his death in his private papers, or they were letters to other intellectuals. Leibniz has a text called Discours de Métaphysique, which is not the name that Leibniz gave it. He didn't give it a name. This was an editor who found it more than a century after Leibniz died. And Leibniz wrote the Discours de Métaphysique in 1686. And the items 5 and 6, paragraphs 5 and 6 of the Discours de Métaphysique, Leibniz talks about complexity. He really talks about simplicity. It's in French. I speak a little French. French is very close to modern French. Fortunately, it's not in Latin. I don't know any Latin. You can actually go and look at this text in French. The paragraphs 5 and 6 are on complexity, and Leibniz does not actually use the word complexity, but he does use the word simplicité. And for complexity, he says for composé, which I think is, as the opposite of simple is for composé. So that is translated as complexity, but if you look at the original text, I think it's important to say that's what he said. So one idea of Leibniz, the idea of Leibniz is very simple, and here's how it goes. Leibniz says, take a piece of paper and with a quill pen just splatter it with ink. So you have a finite set of points on the plane, on this sheet of paper, which are your experimental data. And now the question is, what does it mean to say that these points follow a law? That if this were data from a physical system, this would mean that you found a law, that you understand the behavior of the physical system. So the most obvious thing is to say, well, there's a mathematical equation going through the points. However, Leibniz points out right away, there's always a mathematical equation going through any finite set of points, right? That's obviously the case, especially to Leibniz, who's a wonderful mathematician. The simplest proof is probably what's now called Laplacian interpolation, which actually was afterwards, but since Leibniz invented the calculus, we can assume that it was obvious to him that you can put an equation through any finite set of points. So, says Leibniz, the existence of an equation going through a set of points does not enable you to distinguish points that come from scattering ink at random on a piece of paper, or points that are measuring a physical system which obeys physical laws. So what does enable you to distinguish? Well, he says, if the equation is simple, that's a law. But if it's for composé, then you can always find such an equation, and it's meaningless. So this is the insight of...
But you won't decide that by looking at the points.
Well, that's another problem. That's another problem. Yeah, this is a criterion which is theoretical, but it doesn't mean that it actually enables you to apply it in each case and say, do these points follow a law or not? To actually see what the simplest equation is passing through a set of points. Well, if you limit yourself to an algebraic equation, maybe it is doable.
No, or whether there's a law at all. There's no finite number of experiments you can imagine doing to prove that there's a law.
Okay, in my case, yeah, in this model, the data is given. And you're just trying to understand it, not predict. So I'm trying to make it more closed. But yeah, so yeah, there are all kinds of epistemological problems. This is just a question of understanding what it means to say there's a law, but it doesn't mean we can determine if there's a law or not. Okay, so this idea is mentioned by Leibniz, and Leibniz also says the world is comprehensible. That's in paragraph 5. You have to remember, Leibniz 1686 is the year before Newton's Principia. Modern science is just beginning. It was called mechanical philosophy, and all of the medieval ideas and religion were still very much alive. Modern science had not yet obliterated all opposition. Newton himself was half more in the past than in the future. It was Voltaire who created who we consider to be Newton, the modern scientist. Newton was not a modern thinker. He was more like a Babylonian sorcerer, and believed in theology. So Leibniz, at this crucial moment in time when the old school of thought is colliding with these new mechanical philosophy, says, well, why is the world comprehensible? Leibniz always tried to keep everything good. He wanted Protestantism and Catholicism to be reunited. He wanted to be able to combine theology with modern science and not give up either. But he discusses in the discourse, how can you tell that science applies to the world? That the world is governed by science. And why? And the reason he says why is because of God. I mean, God creates a world which on the one hand is very rich and diverse in phenomena, but on the other hand, all this follows from very simple laws. So he's declaring that the world is comprehensible, the world is beautiful because it follows simple laws, all the richness we see. So this is like a postulate saying that science is possible, the world is comprehensible. So this is, which to Leibniz is a proof of since we're in Jerusalem, I can say it, is a proof of the greatness of God, that this beautiful world is made from a small number of powerful bricks, shall we say, or powerful ideas. It's okay. So this is Leibniz in 1686. Now Hermann Weyl takes this up in his two books, The Open World, 1932, and The Philosophy of Mathematics and Natural Science, 1949, Princeton University Press. But Weyl points out there's a problem, which is how do you measure the complexity of an equation? More or less it's the size of the equation, but mathematical notation changes. Do you allow hyperbolic functions? Do you allow Bessel functions? What notation exactly do you use? And given that, according to Weil, following Leibniz, this concept is very important, very basic, it would be nice to clarify what it is, exactly how you measure it, but it sort of stays in the air in this discussion. And Karl Popper, in a book of his called The Logic of Scientific Discovery, which I think is a lovely book on philosophy of science, Karl Popper has a whole chapter on simplicity. Of course, now we would think it would be better if he called it complexity, this chapter, but it's on simplicity and its opposite, which is complexity, where he basically throws up his hands and said, if Hermann Weil couldn't figure out how to define this fundamental notion of complexity, mathematically, it must be a hard problem. And okay, so this is the prehistory. I view this as part of the interesting prehistory of the notion of complexity of ideas, or conceptual complexity. Now, it's more than 300 years old, right? 1686. So, what happens with these ideas? Well, there is, in my opinion, a way to measure, to take these ideas and make them sharper, to define them mathematically. And the field that does this, I like to call it algorithmic information theory. So, and the basic model of this theory, in my opinion, is the following model of science. Here you have a computer. You give a program to a computer. The input to the computer is your theory, which is software. It's a program. And the output for a computer is your experimental data. Output. And in this model, this is a toy model of what science is all about. Instead of points, dots of ink on a piece of paper and using a mathematical equation as your theory, in this model, everything is zeros and ones. It's finite sequences of zeros and ones. So this is a software view in which everything is a finite string of bits. So in this very simple toy model of what physics or science is about, you have your experimental data and a theory which tries to explain. I'm not interested in prediction. I'm only interested in understanding or explanation. Okay? And the idea is that a theory for this experimental data is a program. All you put into a computer is a program. Any data, input data, is in the program. Okay? So I'm not distinguishing input data from the procedure. It's all put together. So this is your theory. It's a software view of what science is all about. And the idea is that the theory is just a finite string of zeros and ones you put into your computer, it starts calculating, and hopefully it produces output. And it's a theory, an explanation for that data if it gives you exactly as output the string of bits which is your data. This is a very simple model. You can't approximate the data. This is not a probabilistic or statistical view of what science is about. You have to get the data exactly right. Okay, so this is a very simple toy model. But the advantage of this model is that now we can take this insight of Leibniz, and it fits in very well in this model, because now we measure in this model, how do you measure complexity of a theory? Well, by the number of bits in the program, in the software. You see? And we can compare the complexity of the theory with the complexity of the data very easily, because they're both a finite string of bits. So Leibniz's insight is that there's always a theory that's the same size, has the same number of bits. It's just as complicated as the data. And that's useless. That doesn't enable you to distinguish data which follows a law from data which is lawless. So, but if you have a very small piece of software that gives you a very large amount, explains a very large amount of data, that's a good theory. It means you understand. And it turns out with this model, it's easy to show that most finite strings of bits that are data have no theory smaller than their own size. So these would be in other words, most strings of bits, the vast majority are lawless according to this criterion. There is no theory, no real theory, because the smallest program that calculates exactly that string is the same size, really does no calculation, just produces an output, something directly without doing any calculation. Okay, so so this, so in this model, that's one extreme is random or lawless data for which the program has to be the same size and therefore is not considered to be understanding or a real theory. The other extreme is what would the best theory be for data which really does follow a law? Well, it would be the smallest program that produces that data, that explains the data. That would be the simplest theory. Yes?
Are you saying that what you would call simple systems are systems that follow rules?
Well, like this you can distinguish, if this is your experimental data from a physical system, if you view the physical system as a finite string of zeros and ones, this is its behavior as a function of time, say, then you would say that this is lawless or random if the smallest program to calculate it is no better than, is no smaller than, has the same number of bits.
I understand, but how is the notion of complexity applied?
Well, the complexity is measured in the size in bits of the theory. So a small number of bits here means this is actually very simple, and if this is as large as this, then this is irreducible complexity. There is no real theory. And that's the majority of cases. Yes?
This is basically a Turing machine.
Yes, it's a Turing machine.
What about the health problem in Turing?
Well, it's a serious problem. That's a very good question. It means, yeah, what you're pointing out is, I have no way to find the best theory. I have no way to decide if a theory, if data has a theory or not. And I have no way to know if I have the best theory. In fact, that is the main application of this. Okay, so it's a sort of a different viewpoint on the halting problem. So let me tell you that. So the first thing in this theory is, can you find out what the best theory is? That would be the smallest program that gives you that data. Or can you determine if a string of bits has a theory, you know, a program that's smaller or not? And the answer in general is you can't. There's no algorithm and there's no way to prove it. So that gives you an incompleteness result based on this notion. In other words, let me put it this way. One way to put it is call a program elegant. Let me talk about elegant programs. So I'm not going to talk about theories anymore. A theory, an elegant program, I'll define it to be a program that is the smallest, that there is no small, a program is elegant if no smaller, okay, remember I'm not concerned with runtime. I'm only concerned with the size of the program. The conceptual complexity. I'm not concerned with practical complexity issues like time or effort. Just with conceptual or complexity of ideas. So I'll call a program elegant if it is no program that is smaller than it produces the same output. So this would be the best theory for its output. If you use programs as theories rather than equations, an elegant program would be the best theory for its output. Okay. So what if we want to prove that we have the best theory? You know, that a particular program that we're interested in is in fact the best theory for its output. That there is no program more concise that produces the same output. Yes, you're right.
You can imagine several programs with the same.
There may be several. There may be several. I agree. There may be several elegant programs that produce the same output. I agree. There could be a tie. It's true. So let's say we have one of these programs. We're convinced it's an elegant program, but we would like to give a mathematical proof. And the answer is it's very, very hard. This is an incompleteness result, which has as a corollary the unsolvability of Turing's halting problem. So the way you prove this incompleteness result, the proof is actually rather simple, and in some ways even simpler than the original proof of Gödel's incompleteness theorem or of Turing's halting problem, which involve a self-reference. And I don't need a self-reference. I'll show you what I need. The proof of that you cannot prove that a program is elegant in general. So let me give a proof that you can't prove that an individual program is elegant. There are infinitely many elegant programs, of course. For any computational task, there has to be at least one elegant program. There may be many. So there are an infinity of elegant programs. But what if I have a particular program and I want to prove it's elegant? That you can't do that in general. You can see from the following paradoxical program P. Its output is I'm going to have to explain this, but so let me explain this paradoxical program P. So here's how it works. Okay, the output of this program is the same as the output of the first provably elegant program Q that is larger than P is. But let me explain. First of all, when I'm talking about what you can prove, I need to assume that you have what's called a formal axiomatic system, an idea that I think is mostly due to Hilbert, but you can trace it back to Leibniz, Raymond Lull, and you can go very far back with this idea. The idea of a formal axiomatic system is you have a finite set of axioms. You don't use a normal language. You use an artificial language with perfect grammar. You use symbolic logic, first-order logic, usually. And the idea of this that Hilbert emphasized, promoted, was that there should be a mechanical procedure for checking if a proof is valid or not. It should be objective, not subjective. This is the idea that math is completely objective and provides absolute truth. If this is the case, there ought to be a finite set of axioms written in formal logic, and first-order logic is the popular one. And then mechanically you apply the rules of logic to these axioms, and you go through the tree of all possible deductions from the axioms, and this would give you all the theorems mechanically. It would be slow, but in theory you could use a machine to produce all the theorems in mathematics this way.
This is not self-referential?
No, this is just a definition of what a mathematical theory, a formal mathematical theory is.
No, this statement is
Well,
not self-referential.
Well, it's a little less self-referential than I'm unprovable, because all this program needs to know is its own size in bits. You see, so it's a slightly weaker form of self-reference. It's easy for a program to know its own size. It's harder for a program to refer to itself, like I'm unprovable or this statement is false. It's a little harder, although they're well-known techniques. So here's the idea. So we have this notion of what a formal mathematical theory is that I'm going to defeat So Hilbert had proposed the idea of once and for all formalizing all of mathematics, and had said that what it means to say that mathematics provides absolute truth and is objective, not subjective, is that there must be a finite set of axioms and mechanical rules for deducing the theorems from it using mathematical logic, so that it could be done mechanically. It would be objective, and this would give you all the truth. And this idea, Leibniz discusses this idea fairly well, and you can trace back even further these sort of things. But anyway, it's very, very clear with Hilbert, who really emphasizes it. And he really promoted this as a project to once and for all, not to do mathematics this way using a formal theory, because the proofs would be very long, but as a way of saying why mathematics gives you absolute certainty, which he thought to be the case. But we know isn't the case following Gödel in 1931. Okay, so this is an alternative view. So let's assume we have a formal axiomatic theory, and Hilbert wanted one for all of math, but let's just take any formal axiomatic theory. And you just start mechanically applying the rules of logic in all possible ways to the axioms. You start looking at proofs, one statement long, derivations which are 2 steps from the axiom, 3 steps from the axiom, 4 steps from the axioms. And that way you search through the tree of all possible proofs, all possible derivations, and you get mechanically all the theorems in your theory. So as you do that, you look for theorems which say prove that particular programs are elegant, that they're the smallest program that produces the output that they are. And what P does, it's a particular program that inside is basically just a small main program, but this large subroutine which knows the formal axiomatic theory and sets it working. So it's running the formal axiomatic theory, deducing all the theorems, and it looks for theorems. It only cares about theorems where you prove that individual programs are elegant. If you find a proof of the Riemann hypothesis, you ignore it. You just skip over it. And you keep doing this until you find the first proof that a program is elegant, whose size in bits is larger than this program P, keeps going until it finds a proof that a particular program Q is elegant that is larger than P is in bits. So P has to know its own size, which is a self-reference, but not as drastic one as Gödel needed. So what does P do when it finds a program Q that you can prove is elegant in your formal mathematical theory? Well, what it does at that point is it assumes that this theory is correct, doesn't prove any false theorems, and then it starts running Q, and P produces as its output. P's output is the same as the output of Q, which is a provably elegant, therefore elegant program that is larger than P. But this is impossible by the definition of elegance, because P is too small to produce that output, because it's smaller than Q, and Q is an elegant program. Q is the smallest program for the output it produces, and P is smaller. You see? So this means the way to avoid a contradiction, if you assume that all the things you can prove in your theory are correct, the way you avoid the contradiction is that this doesn't work, that this P never finds Q. You see? What this really shows, this would give you a contradiction in pure mathematics if you assume that every theorem in your formal theory is correct, is true, that you can prove. The only way to avoid a contradiction is that P searches for the first provably elegant program Q that is larger than P, but it never finds it because in your formal theory you can only prove that individual programs are elegant if they're smaller, less than or equal in size to P. You see? So what this means is that any formal axiomatic theory that only proves true theorems can only prove that finitely many programs are elegant. And in particular, it can only prove that a program is elegant if that program is smaller in size than the number of bits of axioms in your theory. Because this gives you a way of measuring the complexity of a mathematical theory. I view a mathematical theory as software, as a program again. This is my universal approach. And I view it as a program that runs through the tree of all possible derivations from the axioms and mechanically produces all the theorems. It's an endless computation. And the number of bits in the program that does that is the complexity of your formal theory. And that's, roughly speaking, the number of bits of axioms. It's also the size of the proof-checking algorithm. You know, it's a sort of a natural measure. So if that's the measure of a complexity of a mathematical theory cannot prove that any program is elegant that is larger than its complexity, basically, is what this shows.
Isn't this just a restatement of the incompleteness theorem?
I think Gödel would have been very surprised by this formulation. This is not how this is an incompleteness theorem, but it's a source of incompleteness very different from Gödel's. Gödel's incompleteness theorem is I am unprovable, and therefore it's true if and only if it's unprovable. So this is a very different flavor of result. Gödel doesn't talk about complexity. With Gödel's result, you see, it's easy for people to ignore Gödel. Mathematicians in general ignore Gödel's result and go on working as before, assuming that mathematics gives absolute truth, and assuming that the formal method and formal axiomatics, the axiomatic method is the way to go. And now basically Gödel in 1931 exploded this dream, but people ignore it. Why? Because the assertion he found that is true but unprovable is bizarre. It says, I am unprovable. And this does not look like ordinary mathematics. Now, I don't know if this looks like ordinary mathematics. I mean, mathematicians can ignore this too because they can say, I'm not interested in showing that a program is elegant. But what this does introduce is a notion of complexity into the discussion of incompleteness. So from this approach, not from Gödel's original approach, from Gödel's original approach you couldn't tell if incompleteness is ubiquitous, if it's commonplace, or if it only happens in very strange degenerate cases like I am unprovable, which looks a bit bizarre. But this approach sort of suggests that incompleteness is a more pervasive, is bigger, because it says every mathematical theory has a finite complexity, but the world of pure mathematics has infinite complexity. Just proving that programs are elegant for all possible programs would be infinite complexity. You see? So this makes incompleteness look very natural. It's stated in complexity terms. The world of pure thought has infinite complexity, but any of our formal mathematical axiomatic theories can only have finite complexity. Therefore, incompleteness is natural and maybe should be taken more seriously. Although that's controversial, I believe that. But so this is, in my opinion, the most important consequence of these ideas. This measure of complexity via program size is impractical because I don't care about time. I only care about conceptual complexity. And I don't think it, the idea comes from the philosophy of the scientific method, right? Following Leibniz and Weil. But in fact, I think the most interesting application, in my opinion, is to epistemology, to give you a new viewpoint based on complexity for incompleteness. So I think I still have some time. So let me tell you this is a very simple proof of incompleteness. And incidentally, it has as a corollary that the halting problem has to be, there can't be an algorithm to determine the halting problem, because if you could decide if a computer program halts or not, then you could decide if a program is elegant or not. Because basically what you have to do is look at all programs that are its size or less, decide which ones halt, The ones that don't halt, you can forget about them. The ones that halt, you run them and you see what they produce, and then you could decide if some program that is smaller than the program that you want to decide is elegant produces the same output. So then you could decide if it's elegant or not. But I've just shown you that you can't. So that gives you a different kind of proof of the unsolvability of the halting problem. So this is a different view. What this is I'm giving you a complexity view, but a kind of conceptual or complexity of ideas view of two famous results from 1931 and 1936, Gödel-Incompleteness phenomenon and Turing's thing on the halting problem. But they don't talk about complexity. And the point I'm trying to make is that if you put in this complexity concept, which I think can really be traced back to Leibniz through Hermann Weyl, I mean, I may be stretching the point a little bit, but Leibniz also, he knew about binary arithmetic. I mean, he had a lot of the ideas, let's say. He didn't put them all together like this, but I'm sure he would understand this instantly, but he probably could understand everything instantly, so that's not a... Okay, so the point I'm trying to make is that complexity, this kind of complexity, sheds new light on two very basic results from 1931 and 1936 by Gödel and Turing. Okay, there is a... and this is a very easy proof of incompleteness, I'm sure you'll admit. There is a more dramatic consequence of these ideas connected very closely to the halting problem, and that's the number I like to call omega. So this is a real number between 0 and 1. So the idea sort of here is to take a look again at Turing's halting problem. Turing showed in 1936 there cannot be an algorithm, a mechanical procedure to decide if an individual program will ever stop or not. You can run it, and if it stops, you'll eventually find out. The problem is to prove that a program that never stops doesn't ever stop. And he deduced incompleteness as a corollary of this in his original 1936 paper, because he said if there can't be a mechanical procedure to decide in advance if a program will halt or not, you cannot have a formal mathematical theory that will always enable you to prove for individual programs whether they halt or not, because by running through the tree of all possible proofs, as I just explained, that would give you a mechanical procedure to decide if a program halts or not. If you could always prove it, you could always, by running through the tree of all possible proofs, you could always decide mechanically. It would be slow, but it would work. These are theoretical. Okay, so here the idea is to embed individual cases of the halting problem and in a probability. So instead of asking whether an individual program halts or not, and we know there cannot be in general a mechanical way to decide that, what you do is you look at the ensemble of all possible computer programs. And you ask, what is the probability that a computer program chosen at random will halt? So the halting probability would be 0 if no program halts. It would be 1 if every program halts. And if you're using a real computer or a universal Turing machine, some programs will halt and some won't, so the probability will be strictly between 0 and 1. And there is a technical problem. So a more formal definition is to say that you look at every program that halts, and if that program is k bits long, that adds 2 to the minus k to the halting probabilities. The idea is that I think of programs as being strings of bits. Each bit in the program is an independent toss of a fair coin. So if a k-bit program halts, that contributes 1 over 2 to the k to the halting probability. And the only problem with this is if you do things the normal way, this diverges to infinity.
Sorry, it must be possible. P is the number of times that?
No, P is a program. P is a program.
Small p, what is it?
It's a computer program.
Number of bits.
No, the absolute value of P.
Is the size of the program?
Yeah, this is the size of absolute value of a bit string in general in computer science means the size in bits. Yeah, so this is a program that halts, and this is 2 to the minus the number of bits in the program, because I'm assuming the programs are bit strings. So the only problem with this is a very, because to ask what the probability of the program halts is, you have to put a probability measure on all possible programs. And there's a problem with doing that if you do it the obvious way, the total, it's unnormed. It's a unnormed probability measure. The total probability is infinite, and the total probability should be 1 or less. So that's a technical problem, and there is a solution, and that's the key technical issue in this field. And the way I call it is I say programs have to be self-delimiting, or no extension of a valid program is a valid program. I don't want to get into that because I don't have enough time. But you can solve the problem very naturally, and then this works. So once you can make this sum and get a value between 0 and 1 instead of getting infinity out. So you can define this halting probability. It does depend on your universal Turing machine or the programming language, in other words, your choice of programming.
But if such a measure exists, and you claim that it makes this sum converge,
yes,
it means that you have bounds on this measure, because clearly the measure in front of this 2 to the minus p should be less, that the sum should exist in the limit that p goes to infinity.
It will exist.
You can prove that in fact the measure is bounded
yes.
by 2 to the minus p?
It's bounded by 1. The total measure of this 2 to the minus p over all programs that hold is less than 1. Is less than 1. Yeah, so you can calculate this number in a weak sense in the limit from below. You look at more and more programs, larger and larger size. You run them for more and more time, and that gives you better and better lower bounds. And an upper bound is 1. But this number is in fact violently uncomputable. Even though you can get it in the limit from below, convergence is monstrously slow. It's so slow that you never know how close you are, how many bits are correct in the sum. So you can get it in the limit from below, but only in the weak sense because you never know how close you are. There is no regulator of convergence. Okay, so anyway, this number is actually a very interesting number, the halting probability. And the reason, what makes it interesting is that it shows that there's irreducible complexity, an infinite amount of irreducible complexity in pure mathematics. So let me show you how. In a way, it's an even worse incompleteness result than the one about you can't prove that programs are elegant. I think it's a much better one. So the idea is this. How do I get, where is the complexity in this number? Well, the idea is you take omega and you write it in binary. So it'll be a binary point, and then I don't know. It's a number between 0 and 1, so it'll have no integer part, and it'll have an infinite number of bits. I use base 2 notation, okay? So the numerical value of this, you have to choose your Turing machine or your programming language to get a precise value, but the property I'm telling you about doesn't depend too much on your choice. So once you actually pick a particular halting probability for a particular universal Turing machine or a particular programming language, then you can imagine writing it out in base 2. So the numerical value of this halting probability will be strictly between 0 and 1, and therefore, if you wrote it in binary in base 2, it would give you an infinite number of bits. So these are irreducible complexity in pure mathematics. Because it turns out that each of these bits, as far as we can ever tell, looks very close to an independent toss of a fair coin. I mean, an independent toss of a fair coin. They're algorithmically random. Yes? Yes, sure.
Do you have kind of an interpreter for? I mean, is it easy to find interpreters for the string of bits that would transform it into a program that crunch?
I actually do have a. Okay. It's on my website. It's a Java applet. It has a Lisp interpreter. So this, yeah, I actually did program out this theory to make it more concrete. Okay, but.
You can prove that this is a transcendental number. Is that what you're saying?
It's much worse than a transcendental number. Yeah, it is transcendental. Yes, you can prove that. Yeah, because if it were an algebraic number, it would be highly compressible. Okay, this number has infinite complexity. In fact, each bit of this number is 1 bit of complexity. There is no redundancy here. It's irreducible. In other words, even though this number is well defined mathematically, very simply, the halting probability, by that sum that I showed you, its numerical value is a sort of, given human limitations, it's like a perfect simulation of independent tosses of a fair coin in pure math. Because we can never know the bits. So it's not only uncomputable. I mean, Turing in 1936 already had an uncomputable real. This is sort of uncomputable in the worst possible way. The smallest program, for any number of bits of this, capital N bits, the smallest program for N bits of this, if you want to get the first N bits here out, smallest program also has N bits. And the smallest axioms from which you can deduce what those things are instead of computing them, also N bits. In other words, it's irreducible computationally. The first N bits of this, the smallest program to calculate them will have about the same size, N, for any N. And also, if you're just trying to deduce, have theorems, use axioms to prove what each bit is for the first N bits, to be able to prove what the first n bits are, you will need about n bits of axioms. So this is a irreducible truth. Yes?
If you said 10 bits...
Well, 10 is not serious. Let n be large to get into trouble.
Okay, but 10 bits, in principle,
Yes.
you could be able
Yes.
to write the first 10 bits.
Yes. And a friend of mine, Chris Kaluda, has done that exercise. Yeah.
So can you take finite size programs and then...
For some of the initial bits, in fact, depending on your programming language, you can look at all the small programs and you can get lower bounds and even upper bounds, you know. But very soon you start getting in trouble because of this general result.
Does that prove that the first one is a zero?
That must depend on the programming language.
Well, it depends on the programming language, yeah. You know, as long as the first bits are ones, you can actually prove the initial ones, you can always prove that they're ones by getting better and better lower bounds. So the string of ones at the beginning can't be too long. Anyway, what this says, the idea I'm trying to tell you is that these bits are irreducible complexity in pure mathematics. So in a way, what they show you is that pure mathematics, this is the world of pure thought. So let me say this in Leibnizian terms. Nobody has held up a sign yet? Okay, so I still have a little time. I'm now... Okay, so let me try to use Leibnizian terminology for this, which I think is relevant. Leibniz has a principle called the principle of sufficient reason, which says if something is true, it's true for a reason. You know, and if something is true in mathematics, the reason is called a proof. And if you want to simplify what mathematicians do is they find proofs. Their job is to show the reason, find the reason that something is true. Okay, well, the bits of this number, each of them has to be your 0 and 1. Mathematically, it's determined. In the world of pure thought, it's determined. There's no freedom. This is an individual real number, a specific real number. But it's so delicately balanced between 0 and 1 that we're never going to know. In other words, in a sense, but if we try to prove it or calculate it, you know, one thing is the world of pure math, the Platonic world of ideas, or what God's mind, you know, may contain the value of this number. But for us, the way it works is there is no reason that each of these bits is what it is. Essentially, the simplest reason that the initial bits are what they are is those bits themselves. You know, there is no more concise axiom from which you can deduce this. So, in other words, it looks it's a perfect simulation within pure math of contingent truths, as opposed to necessary truths, because Leibniz distinguishes between necessary truths, which are true by reason, by pure thought. You know, the opposite is a contradiction, and contingent truths like the president of France is Sarkozy. You know, you don't expect to be able to prove that logically or mathematically. It's a contingent truth, you know, or accidental truth, so to speak, or historical truth. And these bits, even though they're in the world of pure thought, in the Platonic world of pure math, are a perfect simulation. They look a lot, because of our finite limitations, like contingent truths. And they look a lot like independent toss of a fair coin. Okay? And what this shows is that pure math is not simple. The way that Hilbert thought, that pure math came from a small number of ideas that we could all agree on, and that's why pure mathematicians think the subject is so beautiful. This makes it look a lot more like biology, say. Even in pure mathematics, we have infinite complexity. Okay? So this is the message I wanted to give to you folks, and maybe it's time to open the floor to questions, discussions. So... I mean, I've been taking questions all along. Does anybody have anything they want to comment or ask? If not, I can go on and talk a little bit more. I think I still have 10 minutes or so. You want to disagree with this, or want me to tell you how the math community has reacted to this? Yeah. Okay. Well, guess what? This is a physics meeting, and I'm being invited to Jerusalem after 30 years for a physics meeting. Really, complex systems is physics, right? Sort of.
Don't tell it to anyone.
Okay. Soren, hi.
About 10 years ago, when I invited you first time, you said, look, I don't accept yet the invitation. First check with the guys in your mathematics department what they say about it, and then tell me again.
And they said, don't invite him. He's crazy.
Now you got the answer. You are slipped towards in the highest possible position. So... it means that finally
okay.
you are the thing.
Well, really? That's great to hear, son. Well, let me tell you how it is. Gödel was basically, at first, caused a lot of shock in the math community. I mean, as a student your age and younger, I would read essays by Hermann Weyl, by John von Neumann, by other mathematicians, and they really, Gödel really disturbed them. It took away their belief in the Platonic world of ideas, in that mathematical truth is black or white and provides absolute certainty. And this upset a lot of mathematicians. And then, strangely enough, such are the powers of the human mind, to suppress, not think about things that are unpleasant. The math community completely ignores Gödel incompleteness and goes on exactly as before in what I would say a Hilbertian style, believing in formal methods and axiomatic methods, or you could say a Bourbaki style if you want to use the French school that came from Hilbert. And this is still the official religion in the math community. And the math community, their reaction, the logic community, for example, the reaction to this work is, first of all, they think it's crazy because they don't understand these concepts of program size, which are really connected to entropy, complexity. To them, these are very strange ideas. And to talk about something that imitates randomness, in mathematical logic is heresy, because logicians are people who hate randomness. That's why they became logicians. So even Gödel incompleteness is unpopular in the world of logic or in the world of mathematics. If you look at the reaction of the logic community, mathematical logic community, to Gödel is very ambiguous. On the one hand, they have to claim him because he's the most famous logician ever. So they have to claim him. But on the other hand, if you look at Gödel's incompleteness theorem, what it obviously says is that logic is a failure. And therefore the subject can be thrown away and you don't have to teach any more courses. And this, of course, no logician would like you to take home as a message from a course on logic, that they should fire all the logics professors. So normally books on logic have the last chapter may talk about incompleteness, and of course, as you know, you never get to the last chapter when you give a course. So these ideas, those physics, these ideas are really very close to ideas from physics. This is the idea of looking for randomness in pure mathematics. Randomness as lack of structure is connected with entropy. These are sort of versions of ideas, statistical mechanics. These ideas are, to physicists, these ideas seem much more familiar, and their physicists are much more comfortable with this, which is why here I am at a physics meeting, not at a pure math meeting. So I would say, but I think, to stick my neck out, I think that what this really shows you is that pure mathematics is not like theoretical physics, but it's not that different. I mean, pure mathematicians like to think that they have absolute truth, and we physicists, I consider myself an honorary physicist, so we say, our proofs are just heuristic, they're unrigorous, they're worthless. But my feeling about all of this is that it's a continuum. Absolute truth you can only approach asymptotically, in the limit, and there are heuristic proofs of the kind that a mathematical physicist feels comfortable with that are not rigorous proofs, and it's a continuum. I don't see a sharp divide between the world of pure mathematics and the kind of reasoning that a theoretical physicist would be happy with. I mean, it's nice if you can have a rigorous absolute proof, but what would be the other extreme? If you take Gödel incompleteness very seriously, you could say, I have a property of the prime numbers which I checked on the computer, and there's a beautiful curve, and it's fit beautifully by a very simple equation, and a physicist would publish this, right? And a pure mathematician will say, I don't care how accurately this very simple formula fits the curve, and it works out to 100 billion or a trillion. I need a proof. And so what happened is a few mathematicians have been promoting what they call experimental mathematics. There's a Journal of Experimental Mathematics. There are a few books on experimental mathematics as a research methodology that, for example, John Borwein has co-edited these books. And he's not as extremist as I am. I think what this does is provide some theoretical grounds for thinking that maybe pure math is quasi-empirical, I would say, Lakatos. And let me say that there are cases in the world of pure mathematics and theoretical computer science where people have behaved like physicists, adding unproved hypotheses. P not equals to NP is such a case, time complexity. In set theory, which is a very abstract axiomatic set theory, there's a thing called the axiom of projective determinacy, which is now being added to the usual axioms. If you look at mathematical cryptography, which is a very popular subject in theoretical computer science now, they can know there is no case for which you can actually prove that a cryptosystem is secure. And the way the proofs work is they are based on unproved hypotheses that the community sort of agrees on and could theoretically be refuted at any moment. Typically, they're based on the idea that to factor a very large number takes an amount of work that grows in a certain way. And so these people, P naught equals to NP, some of the ways that people work in mathematical cryptography, the way that axiomatic set theorists are working, in a way it's like a theoretical physicist would work, in that they add new axioms which are pragmatically justified because they help to organize the field, but they're not self-evident. You know, normally you think an axiom has to be self-evident or a postulate. This is sort of the classical view of an axiom. Yes?
What do mathematicians think of the continuum, the fact that the continuum hypothesis cannot be proven? Do they believe it? Do they think it's relevant work? Cantor is an idiot?
Well, you know, if you look at a guy like Pfefferman's a logician in the United States, his view is that set theory is dangerous. And his view, Stanford, you know, there are people, set theory is a problem, is a thorn in the side of mathematics, because it leads to so many paradoxes. That's my talk on Wednesday morning, I suppose. You know, even the latest version of axiomatic set theory, which adds a new axiom called the axiom of projective determinacy, which is very non-obvious and non-intuitive, but all the experts, you know, claim now has to be added. It does not, I don't understand this field, but the article by Wooden in the Notices of the American Mathematical Society, the 2 survey articles, it still is not powerful enough to settle the continuum hypothesis. So with this viewpoint, you know, I would take a much more slapdash, playful attitude in pure math, like you do in physics. You know, in physics, high energy physics, people propose new theories every week, right? And most of them are wrong. But every now and then, the community sees that a certain line of attack is promising, and they pursue it. And, you know, I'm not saying that all mathematics should be done like that. If you can have a rigorous proof, it's wonderful. But what these results suggest to me, based on complexity to incompleteness, is since pure math has infinite complexity, it may be the case that there are lots of things we would like to prove but can't. That's what these results tend to suggest. In which case, maybe pure mathematicians should feel freer to behave a little bit more like physicists. Yes, Imre?
Isn't all this incompleteness related to the way the human brain works? Aren't there efforts to understand from a cognitive science or neuroscience point of view of the way we produce proofs, we reject bad ideas, whatever, and then it might be related to the fact that we are not able to reach every single conclusion which is right, but from a given starting point we are not able to reach it.
Well, you know, how human creativity actually works is a very interesting subject, and I don't know that this work has much to do with it.
It's like a high temperature Monte Carlo.
Well, this model says that no mechanical approach can give you all the truth and has limitations. But
that is precisely what I'm trying to say.
Yeah.
It works like zero temperature Monte Carlo.
Okay.
Logic reminds me of this type.
Yeah, so what we need, Imre, I think we would agree on this, would be a kind of a new meta-mathematics which would talk about how creativity actually works and how mathematicians make progress, because these results are very negative, and you might think that mathematics couldn't work at all with the incomplete results and the truth is that mathematics is going along splendidly, and so it would be interesting to understand how the human mind functions and why mathematicians are so creative and it works so well in spite of these pessimistic results. So I agree, I have no idea, but I agree with you that I think it's an important thing.
Long ago I read I'm not able to remember the source, but I read some paper on this type of studies of the working of the neural system. That somehow we are producing basically random proposals, and there is a function and there's something sitting in the right hemispheres or whatever, which is selecting the ones which we are willing to accept.
Well, it's not completely random. I mean, your intuition at night, your subconscious is...
Yes, something which has a lot of excitation about it.
Yes.
And that would help you across these barriers and land.
Yeah. I think it would be very interesting to try to come up with a theory of a positive theory, a positive meta-mathematics. Instead of an incompleteness result, try to come up with some understanding of why mathematics, in fact, does so well, why mathematicians can do so well. And so I would agree. I wouldn't be satisfied just with cognitive science. I would like a mathematical theory describing how mathematical creativity works. Since I'm a mathematician,
isn't there some kind of
paradox?
in mathematics and the neural system? Do you believe in this Platonic phantasmagoria?
Well, yes, I guess I do.
There are a few approaches.
Well, this result becomes meaningless. I mean, the game I'm playing is in the Platonic world because it's very impractical. I put no time limit on. Ask whether a program is elegant is meaningless if you take a down-to-earth approach, because I don't put any time limit on the time the program takes. And if you put a time limit, it's trivial to see whether a program is elegant or not. So the same with Turing's halting problem. From a practical point of view, that's... Yeah, so this is the game that I'm playing here. You can view this as an approximation. This is a very unrealistic theory. The reason you mathematicians, we like to work with toy models, oversimplified models, is because we like to try to prove things. So this model of what science is about or what mathematical reasoning is, I agree, it's a toy, it's a caricature. The only reason you do it is because it's simple enough that you can prove a few results. Now, hopefully, the reason you do it is because the hope is that this oversimplified theory will give you some hints as to what happens in more realistic cases. But it may be misleading you. But this is what this is. I would call this, Picasso said art is a lie that helps us to see the truth. I would say theories are lies that help us to see the truth. So this model, I agree, is a caricature of what the scientific method is or what mathematical reason is. But the advantage is I can prove a few results. You see, but you have to decide whether to take these hints seriously or not. Whether they're typical or atypical. You have to decide whether they can apply in more down-to-earth situations, and that I don't know. I think I should stop here. Thank you very much.